So in the next hour now, I'll be giving you a quick introduction and tutorial on the Creo Generative Topology optimization. So introducing what is GTO? Well, firstly, just to explain the Creo Generative Design Strategy, there's actually two parts to the Creo Generative Design product line. What I'll be showing you today is GTO. And you'll see how we can actually specify some basic geometric requirements. We can apply loads and constraints and material properties. Then we can let the software actually create what it estimates to be the most efficient design to meet those requirements. And then that can go to other forms of analysis and so on. So Creo GTO is a desktop package, so it runs locally on your laptop, desktop, etc. But there is also a version of it called GDX, and this actually runs in the cloud. So you start off on the laptop product, on the local computer product. You set up the model, but then you can actually upload it to the cloud. And because it can run on the cloud, you can run many more different versions of your design, all basically at the same time. And then you can set up some complex objectives and filtering functions that will actually help you to choose what is the best design. For instance, which design is strongest, which design is cheapest, which design is easiest to manufacture. So you can actually look at various different criterion based upon this cloud version of the software. And then when you've chosen your design, you can download it back onto your local PC and you can go and do other analysis types with it. So with GTO, we start off with a kind of a simple block, and then you'll see it can be optimized into a variety of different shapes. Now, these different shapes tend to depend upon what are the loads, the constraints, and also what are the manufacturing requirements. Is this part going to be manufactured with additive manufacturing, or is it going to be created with casting or plastic injection molding, or is it going to be machined? So depending upon the manufacturing requirements and also indeed the materials, the design may end up being quite different. But one of the unique capabilities of GTO compared with other topology optimization software is the fact that at the end of the process, we can actually turn it back into a CAD model. Now, most topology optimization software uses a finite element type method, but what you get out at the end is either a finite element model or something like an STL, surface triangulation, and those are fine, but you can't actually use them for kind of downstream CAD applications, like integrating that part that you've optimized with other parts in an assembly. But with GTO, the output of the software is actually a Creo geometry. And so this can then be used in assemblies. You can go on to do other types of analysis on it. And that's, I think, one of the great strengths of this product. Now, this slide was actually produced when the software came out. There's a kind of a countdown. The goal is to be able to do optimizations for structural, thermal, and modal. Well, currently we've got structural and modal, but thermal has been delayed, so we're hoping to see thermal next year. But anyway, I'll be showing you examples of optimization for structural strength, for instance, that strength and stiffness, and so on, and also modal analysis. In modal analysis, what we try to do is to make sure that the first natural mode of the structure is as high as possible, which helps to avoid problems with low frequency vibrations. So as you'll see in a few moments, we basically have three types of geometry when we are working with this software. We have what's called the starting geometry, and in this case, that's this kind of envelope. Sorry, that's not right. That's this envelope that you can see going around the outside. So the starting geometry is a body which represents the space that is available for creating your optimized design. And that's the transparent region here. So within that, we have a number of regions, what we call the preserved geometry. Now, these are regions where we know we need that geometry to be a particular shape. Mainly, these are locations where we apply loads or constraints, or this part is connected to other parts in an assembly. So those are parts that will remain fixed during the optimization process. Now, the last main geometry type here is the excluded geometry. Now, excluded geometry is something that I haven't seen in other tools like this. What it is, it's a kind of a keep out region. If you know you don't want the optimization to go into certain areas, you can use this as a kind of a keep out function. Now, it used to be that what we used to do this was we would just actually take a chunk out of the starting geometry. So it's still possible to do that, but there's actually a number of computational problems when you try and make very complex starting geometries with lots of internal cutouts and regions. So the excluded geometry function is actually much faster and much simpler to use, and it gives you much better results. And then, having set up the starting geometry, the preserved geometry, and the excluded geometry, we can set up other things. Now, it's probably a bit small on the screen here, but we can set up what are the design goals. For instance, do we want to minimize mass, or do we want to minimize stress? And we can also specify geometric constraints. We can specify, for instance, symmetry. And as I'll show you one of the examples, if we have time, we can have planar symmetry, or indeed in the latest version, we can have a rotational symmetry. So if you were designing something like a cast wheel with multiple spokes, you can actually do that using rotational symmetry. And also what's very important is the manufacturing constraint. So as I mentioned earlier, we can specify the manufacturing can be for additive manufacturing with a build direction. It can be for casting or molding with a parting line. It can be for machining and a few other types of options here. And then lastly, down the bottom, we have the materials. So I'll show you this in the examples, but you'll see it's a relatively straightforward process. And then we run our optimization, which is in this software is amazingly fast. And then we can actually go through and look at the results. So we can go through and look at stressors, deformations, modal frequencies, things like that. And we can just do that to check that the design is really meeting our requirements. And then we actually output the result and convert it back into a CAD model. To run Creo simulation live, you have to have a GPU. Now, GTO does not require a GPU, but if you have a GPU, it will run faster. So what we recommend is that people who want to use either Creo Simulation Live or GTO use a laptop or a workstation with a Quadro GPU. All right, so I'm going to switch now onto my Creo window, and I'm going to load an example. This is actually the first tutorial from the training course. So as you can see here, what we've got is some type of a mounting bracket, and it's got a shaft or a pin going through it. Now, I'm actually just quickly going to switch into the Creo live simulation because I've already set up a basic structural analysis on this model. And this illustrates what's going on here. So you can probably see that I've got constraints on the 3 holes that are in the base plate of this bracket. So I've got my constraints there, and I've also got a force which is pulling up on the surfaces of that pin or shaft. Hopefully you can see the arrows pulling up there. So I've got a constraint and a load, and obviously this is enough for me to do a basic structural analysis. So now with Creo Simulation Live, all I need to do is to press the simulate button, and then in just a few seconds it will actually run the simulation. So as you can see, I've already got the results there. So this is the strength of Creo Simulation Live. This ran in less than a second. We're looking at deformation now, or I can look at the stress. Now what we can see in this example, there's actually quite a high stress on the shaft, but on the bracket itself, the stresses are very low. For instance, if I go and poke in this corner here, I'll see that the stress is only about 9 megapascals. Now, if this is made out of metal, this is probably about 1/10 of the of the stress that we would be expecting for a metal bracket. So so that means this bracket is much too strong, much too heavy for this application. So in that case, this is why we really want to go to do some topology optimization. Now, the other thing to notice about this bracket is that it has multiple bodies. It has what we call the envelope, which is, as I mentioned earlier, this is the region that is available for optimization. This is also within GTO referred to as the starting geometry. So the terms envelope or starting geometry is effectively the same thing. We also have 3 different bodies for these 3 constraints. So you can see there's a kind of a cylindrical green body that's located around each of the constraints. And there's another body for the shaft that's going through it, and another body for the kind of this almost like a bearing or something where this load is being applied. So this is a multi-body part. Now, in case you're not familiar with the multi-body capabilities in Creo, we have all these capabilities for creating and editing multiple bodies. So for instance, when you're creating a new feature, something like that shaft, when we're actually creating a new feature, this is a single part, but you see we have this section in the part creation dialog, which allows us to actually tell it to create a new body. And that means that that new protrusion or whatever feature you created will actually go into a new body. So this is how we construct multiple bodies. And it's a requirement for you to create multiple bodies. Now, in case you were wondering, oh, why can't we do this with an assembly? Unfortunately, at the moment, GTO does not work for assemblies. So all we can do at the moment is optimize parts, but we can approximate the behavior in assembly by creating multiple bodies within a part. So this is kind of like an assembly, but it's actually all within one part. So we've got this multi-body part. We've seen from the live simulation analysis that it's actually very low stresses on the bracket. So what I'm going to do now is to switch into generative design mode. You can see here up on my applications toolbar, I've got a button for generative design. So I'm going to pick on generative design, and now I can see this model I've already set up. So you can see that that outer region, the envelope that we defined, that has been specified as the starting geometry. So we've got starting geometry, and the preserved geometry is those three constraints and the region where the load has been applied. Now, there is this additional body, there's this sixth body, which is the shaft. Now, this is actually not currently specified in the model. Now, this means it's a kind of an associated body. So this is like, this can be used, for instance, to represent if you had an assembly and the part you want to optimize is connected to some other objects. So you can create a representation of those other objects and the loads and constraints that are on those objects as these kind of unassociated bodies. But because this body is not associated, we need to specify a contact between this kind of outside body and the region we want to optimize. Now, one important thing to note here is that the connection here, the contact definition, is between the shaft and the envelope. Now, you might think logically that your second reference would be to the blue preserved region, which is surrounding the shaft. But those preserved regions are only there as a reference. What we're actually optimizing is the envelope. So in this case, the contact needs to be between the shaft and the envelope. Now, you can also see here, I've got a structural constraint, I've got a structural load case, and I've got my constraints. This is exactly the same constraints as were defined in the Creo simulation live model I showed you earlier. We've got the constraint, we've got the load. Now notice in this example, I've just got one load case, but we can actually have multiple load and constraint cases. So in this case, it's a load that's pulling up, but I, for instance, might have another load case that's pulling to the side or pulling, to the front or back. So we can actually create multiple load cases. And then during the optimization process, the software will try to find the best design that meets all of the requirements from the different load cases. So it's an optimum of all the different load cases. So the design should be able to work under all kinds of load conditions. Now, in the design criteria section, we've got, in this case, the criterion we're selecting is to maximize stiffness. So it's going to make this model as stiff and strong as possible. But we've said that in this case, we've given it a target, and that is to reduce the bracket part to the envelope to 30% of its original value. This 30%, by the way, it refers to the region of the envelope that's outside the preserved regions. So it's the transparent gray area that you see. And in this case, we want the final part to be symmetric. So we've got planar symmetry. Now we could actually include a number of other types of condition. So for instance, here, in fact, we could have chosen rotational symmetry or a kind of a patterned repeated symmetry. This is like a linear pattern, a series of objects in a row. We can also choose, if it's for additive manufacturing, we could choose the build direction. For casting or molding, we choose a parting line, or for machining, we would probably choose an extruded direction, and then for instance, we could put a draft angle on it, and that can also apply to casting. And the part here, the material we're going to look at is steel. By the way, in this section on materials, you can actually add in a whole list of different materials. And if you're using the GDX version, it will automatically run through the whole list and analyze the part, optimize it for each of the different materials, and it'll do that automatically. Anyway, so I set up my my design criteria here. There are a few other settings that we can change. We can set up a few control parameters, but generally we just leave these on the default settings. We have this button here for the troubleshooter, and basically this tells me, there's a little green dot on it, this tells me that everything appears to be fine with my model. If you've made any mistakes, it would try and estimate what they are, and it would actually show you a description of what it thought the mistake was. Probably the most common mistake here, by the way, and I should have mentioned this earlier, is for people to build an envelope, but the preserved regions somehow stick outside the envelope. It's actually a rule with this software that these blue regions must be inside the envelope. The shaft here, which is this kind of unassociated region, this can stick outside the envelope, but the preserved regions must be actually included within the envelope. Because, as I say, the optimization can only occur within the envelope, and the preserved regions are those which must be included. So by logic, you have to have the preserved regions inside the envelope. It would be nice if the software did this automatically for you, but it doesn't. Now, you might also ask, well, what happens if I don't have an initial idea for my starting geometry? I'll come back to that later, and I'll show you how we can also look at that case. But now I'm just going to press the optimize button at the top, and this is now running live on my laptop. You can see it started with the full geometry, and it's already finished. It's a bit embarrassing sometimes how fast this software is, because people think I'm cheating. I'm not. It actually took 6 seconds. And this is a laptop. Okay, it's a good laptop, but it's a laptop. But almost any one, but it's a 3-year-old, 4-year-old laptop, so almost any modern laptop or workstation will be faster than this. And you can see it just had a little report up here. It says it achieved the design criterion. For steel, it was able to reduce the mass to 30.5% of its original mass, and this is the average mesh sizing, and this is the CPU time that's involved. Now, having done that, we can go through to look at the results, and just as I showed you with Creo Simulation Live, we can look at the stresses here. We can look at the displacements. So I've got von Mises stress and displacement here. So I can see this. And obviously I can check this out. Am I happy with the design? If I'm not happy, obviously I can go back in and maybe make a change to the to some of the parameters. I might change the design criterion. I might say, oh, this looks a bit too skinny, so maybe I'm going to try and add on some more mass, or maybe the other way. Maybe I want to make it even lighter than this one and remove more mass. So we can change the design criterion. But assuming that I'm happy with this design, I can then go to press the button up here, this one up here, to generate the design. So at the moment, this kind of greenish shape you see here is actually the result of a finite element simulation. Now, traditionally, these are output as a kind of a tessellated format in normally exported as STL format. What I'm going to do here, I'm going to create a new part, and I'm going to tell the software to actually reconstruct the geometry. So it's asking me for the name of a new part. I'll just give it a simple name. And it's now analyzing the surface of this optimized geometry, and it's actually going to wrap a Creo free-form surface around that geometry. And it's then going to intersect the optimized geometry with the let me just change something here that I don't like. Yeah. Oh, so it's actually intersected the optimized geometry with these preserved regions. Now you can see here it's a very nice quality, very smooth surface. It produces beautiful, smooth results, this. And this part, I need to emphasize, this is a Creo part. You can go and use this as an assembly. You can cut holes through it. You can add on protrusions. And one of the really neat things about this is that this is actually, this free-form surfaces are actually editable. So I can pick on a surface that I maybe want to make a change, and on that surface, I can go to drag it around. I can tweak it. I could twist it. I could roll it. I can pull, say, for instance, I wanted to make a bridge between this left-hand constraint and the right-hand region. I can actually create a kind of a sausage-shaped region that would actually connect these two together. So this has the full power of the Creo surfacing, surface geometry editing functionality. So this, as I say, I need to emphasize this is a fully editable CAD solid. We can go here and we can go to look at its mass properties. I should have actually checked this earlier, but we can go to look at its mass properties. We can see its mass, its volume. It's a Creo part. And indeed, if I go to my live simulation mode, I can press on the live simulate button again, and now it's going to run my simulation live software on the optimized part. So I don't know about you, but I still find this pretty amazing. I've been using this for several years now. All right, great. So that's the basic setup of how to do topology optimization using Creo. Now, one thing I want to mention here is you might ask, for instance, what happens if I don't have a starting envelope? So let's actually just remove that. Now, can you see what's happened there? Let me just make that. I'm just going to hide that body a moment. That envelope now, I'm going to convert it to a construction body, and I'm going to hide it. Now, there is a problem now because the original contact, you may remember, was defined between the shaft and the envelope. But now there is no envelope. So we need to actually redefine the contact here. So I'm going to delete the contact. But what I'm going to do, I'm going to edit this here, and I'm going to apply that load to the actually directly to the inside of that preserved region. So that should be the case now. Let me see what now. Also, I can't use that option to set it to a certain percentage of the starting weight because there is no starting weight. What I can do is to set it to a particular mass. So say that I want to reduce this bracket to about 1.5 kilos. Now I've got an explicit goal for the simulation, and I can go and press the optimize button again. And you can see it starts off with that original envelope shape, and it's now optimize my model again. So again, I can see I can see this shape. The shaft isn't moving because I've disconnected the load from that. But just to explain, this is for, you know, people who haven't, who don't have a starting envelope. However, what I would say is that although you can do this, you don't have a way to control this automatically created envelope. It's just created to a certain, like a certain amount around the existing preserved regions. So if you want to control this, you actually need to create multiple, say for instance, you want there to be a nice clean hole. Now, probably you can see here, the optimized geometry is actually spread into the hole here. So this is obviously not what you'd want. So this is why we would need in this case to actually create an excluded geometry, and we would need to create a cylindrical region through each of these mounting holes that was an excluded geometry. So I think that leads me on to show you the second example, which will make it more clear what is an excluded geometry. All right, so I'm coming on to the second example now. Again, these are the standard examples that are included with the tutorials. So I'm going to go to my example here. So again, this is a multi-body part. We've got the envelope is this kind of, you know, it's the outer blocky region. I've got a couple of shafts which are sticking through this, and I've got 3 preserved bodies. If I just hide the envelope a moment, you can see I've got a preserved body. This is going to be where the constraints are applied. And then I've got these other preserved bodies where the design intersects with those shafts. So let's turn this on again. Now, also, it's hidden at the moment. I'm going to turn on. I'm going to say that this region here, this region in the middle, this is a preserved region. So I want this to actually be moved outside. This one is like a keep out area. So I want to make sure that the optimized geometry is outside this region. Now, again, I can do a quick check on this model. And in fact, in this case, I've actually got two load cases. So I've got a load case here, which is the loads are trying to pull the 2 pins apart. So one is pulling to the right, the other is pulling to the left. Also, I've got another load case where there is a vertical loading on both shafts. Let me see, have I done something wrong here? Just a second. This one I think needs to, they changed the software and it needs to be redefined. Okay, yeah. So I've now got an example here where it's showing deformation, and I can see how it's actually bending up this geometry. So these are the load cases that I currently have. So I'm going to go into my topology optimization software again, and I've got my my starting geometry, that's the transparent envelope. I've got my preserved geometry, that's the blue regions. I've got my excluded geometry, that's the red region. I've got my 2 constraint and load cases. I'm just going to check that this one is running okay, because I had to make a slight change there. So I'm just going to check with GTO that this is running. I think I actually need to change. They made a slight change to the software before, so I'm just needing to make a small change to the geometry, to the loads here. I think this one should work a bit better. So I'm just running an initial analysis, and yes, I can see that I'm getting that that bending behavior there. So that's running fine now. So what I can do is I can now go into the full topology optimization. So this is optimizing away at the moment, and you can see now that this geometry is coming up with a very interesting, very nice, quite complicated shape. This example here was actually set up with two different design criteria. The first one here was for additive manufacturing, so it has created a geometry which can be manufactured by additive manufacturing. So I can see here, again, I can look at my optimized shape now. I can see it behaving. Maybe I'll just go to hide that exclude region. So I can see now there's this kind of you can see where the exclude region kept the optimized geometry out of the middle. I'm looking at the optimization from load case 1. I can also look at the optimization result for load case, sorry, that was load case 2 first, and now I'm looking at load case 1. So we can see that it's optimized for the two different load cases. And again, I can go to generate the design here. What I'll do quickly, okay, sorry, just before I do that, I wanted to show you that there is a second option here. The second design criteria here has actually got, this is for a part to be machined using simple, simple kind of 3-axis machining, and it's been specified for machining. We've given it a build direction, and also there is an extruded angle, so we can actually give it a bit of a draft angle on the final part. So just to save time on this, I'm just going to open the optimized part. So I'll show you the optimized part from the for the additive manufacturing. So you can see here, this is my part that's been reconstructed. It's pretty sweet. And again, I can go and do my Creo simulation live here and look at it. And also I can get rid of this one, and I can open the other one, which was optimized for to be manufactured by machining. So you can see now this is a part. It doesn't have any overhang. In fact, the whole thing actually has a minimum draft angle of the value I specified. I think it was 5 degrees. So the minimum draft on this is 5 degrees. It's even added a draft around the preserved regions, which were originally parallel sides. So that's an interesting thing to note. It's actually not only optimized geometry, but it's actually fixed a problem with the original specification. So that's a nice example that shows the a few additional things: multiple load cases, excluded geometry, and so on. So so what I'm going to do now is to show you a couple of other examples, well, actually 3 other examples, which will give you an idea of some of the newer capabilities in the software. So I'm looking at this one example here, and this is an example for optimizing the first modal frequency. Now, this is an interesting model because we've actually only got 2 bodies we can see. We've got this inner hub body, and we've got an outer body, something like a wheel rim. In fact, there is actually a 3rd body here, which is like a shaft, and that is going to make sure that the optimized geometry doesn't cover this kind of hub in the middle. So we've got this here. So again, I'm going to switch into my generative design. You can see the setup here, and oops, all right, it's already loaded the results, because this is actually a modal analysis. Now, modal analyses do actually take a rather longer time. So this example here actually took 28 minutes to optimize. You can see here there's this red region. This is acted to make sure, and you can see that it's made sure that there is no geometry interfering with that hub region. But it's actually allowed the optimized structure to actually spread out on either side of the rim and the hub. Let me just hide that part a moment, and then we've got this optimized shape, and I'm going to come on to show you the results. And now what I'm looking for is the different modal frequencies. So I'm going to animate my my analysis here. So the idea of this optimization is to make the first natural mode, for an eigenmode, as high as possible. This is the best way to reduce the risk of vibration in a study. Incidentally, just zooming up here, you'll notice up in the left-hand corner, I have these two options here, structure study and modal study. So this has been created as a modal study. So again, zooming in here, I can see that this was a modal study. And in a natural mode study, we just have normally have some fixed region. So this is the rim in this case. And I've also got a cylindrical pin connection for this middle hub. So this model has been set up. The actual design criteria in this case is to minimize mass, but to maintain the fundamental frequency. The first eigenmode needs to be greater than or equal to 3. In fact, it's actually probably going to be much higher, but it will maintain the highest eigenvalue it can. So again, coming on to look at the results there, I can see that, in fact, the first mode is actually, this is a very stiff model. It's actually up at what's that, 4,300 hertz. So this is a very stiff, very high frequency. Actually, was that limit? I can't remember. Was that 3 hertz or 3 kilohertz? Yeah, sorry, it was 3 kilohertz. So this is said that I was thinking 3 hertz, that's a bit low. But this is actually this wants to set the fundamental frequency to be greater than 3 kilohertz within this region. So it's worked out that the stiffest design that meets that requirement within the available space is this. Now you can actually combine a static study with a modal study. So you can actually create an optimized design that is optimized both for static loading and also for dynamic loading. All right, great. So let's close that one and let me see what else we've got. I just clearing out my memory from the background. There's another one here. It's actually quite similar to the one we saw earlier. So this is pretty similar to the one we saw earlier, but this one has actually got, this is something that was introduced actually, I think was it? Yeah, it was last year with, oh no, hang on, sorry, it's this year. Yeah, this is a new feature in Creo 10 that you can actually specify a factor of safety for the software. So, so this material here in this case, previously it was steel. This has now been specified to be made out of a titanium alloy. And we can see here for the titanium alloy material properties that its tensile yield stress is 940 megapascals. So the idea for this model here is it's going to optimize the stress to be, so there's a safety factor of 3 between the maximum stress on the optimized region and the material initial yield stress. So basically it's going to aim to have the maximum stress being 940 divided by 3. So what we can see here is indeed that it has optimized it to 314, almost 315 megapascals. So this has analyzed it so that this maximum stress location here is basically, you can see this is the maximum stress here, yeah, about 310. So this maximum stress at this region, it's got a safety factor of 3 between this and the material initial yield stress. Okay, so that's something new that's introduced in Creo 10. There's actually a bunch of other features, but I don't really have time to show them. And just for the final one, that's quite neat. This example here, this is actually from one of the larger Creo demos, but we've got this part. This is actually the tail rotor assembly from a helicopter. And you can see it's got this kind of hub part, which is where all of the or the veins or blades insert into. Sorry, let me snooze on that. Now, this is the original design. Let's just open that up, and you can see here it's got a number of stiffeners, things like this in it. When we go to do a live simulation, we can see that if we load up one of these blades, we can see that there is a maximum von Mises stress of around, let's see, megapascals. We have a maximum von Mises stress of around 300 megapascals. This is actually a pretty high stress, and because this is a safety critical component in an aircraft, this is actually a problem. The stress here is much too high. So what we would like to do here is use our topology optimization to produce a part which is lighter, stiffer, and stronger. So I'm going to get rid of that part. And to save time, I'm going to load another part which I've already set up for this. So this is my part that's been set up. Now notice that this part here, it doesn't have any stiffening ribs in it. So if we just actually look at this as it is, it's actually going to have an even higher stress than the previous one. So the maximum stress here with this design without the stiffening stress, this is 427 megapascals. So this is not good. But what we're going to do is to go into the generative design module, and we're going to optimize this. So this has now been set up. It's got the appropriate starting geometry, preserved geometry. There are, we've got some, sorry, they're down here. Where are they? We can see there are some preserved regions here. So we've got the regions where other components need to fit in. We've got these preserved regions. Let me just hide them again. And in this case, the design criterion is set up for rotational symmetry. So we've got, this icon is rotational symmetry, and we've said we want there to be 9 instances of this around the rotational axis. Now, there are 9 vanes here. There are 9 holes in this plate, as you can see. So obviously it's going to try to produce an optimized shape that is that fits within all those holes. So now I think probably to save time, because I'm running past my allocated time now, I'm just going to load the result of the optimization. But I did run this earlier and it only takes a couple of minutes. But let me just go to open this and let's see the optimized part. So this now is the optimized part, and you can see here these additional arms that have been added to the geometry to strengthen it. So the final part here is, in fact, the original part was just over a kilo, but this part now is also actually just about a kilo, so it's actually kept the mass the same. However, if we go to do a simulation on the optimized part, so we're using our live simulation again, what we'll see here is that the maximum stress is now down to only about 100, just over 100 megapascals. Let me turn up the accuracy on this. It's a bit rough as it is, so I'm just turning up the accuracy on this solution. It takes a little longer, but we can see that the maximum stress here is, so where are we? The maximum stress is 127. Now remember, our original design was 300 and something. The starting point for this design was actually 400 and something, but the final design now is the same weight as the original, but the stress has been reduced essentially to 1/3 of the initial design. So we have a design now. It's the same weight, but it's 3 times as strong, and it's also got rotational symmetry, so it's perfectly suitable. And we could now, in fact, go back into our assembly and we could insert this part back into the assembly. All right, now there's many other things I could show you, but I just thought this would be these would be some interesting examples for you to get an idea of the capabilities of the software.